Hello everyone, welcome to this online course on material science. This is lecture 2 in the module 2 on superconductivity, and in this lecture I will follow these two textbooks. One is the Quantum Theory of Many Particle System from Fetter and Waleka, and the second one is the one that I have used in the first lecture from James Annett. My plan here in this lecture is to give you some experimental facts about superconductivity. Because if you recall, in the first lecture I have mentioned that the discovery of superconducting effect was made by Camerling-Owens in 1911, right? And then the microscopic understanding why material superconducts came in 1957. So it took a really long time to understand the effect of superconductivity. And during this time, there are many experiments were performed on superconducting material to understand what really can be a possible theory for this phenomena, right? And the first experimental fact that I have already mentioned in the first lecture, but let me mention it here for completeness, is that for every superconducting material will be characterized by some critical temperature, which is known as Tc, which is also the superconducting transition temperature. And what happens really is that in your experiment, when you are above this temperature, the material that you are probing is in the normal state, right? But as soon as you go below this transition temperature, the materials become superconductor. That's how you define the conducting material with a Tc. And below that, the electrical resistance vanishes. So the resistivity vanishes to zero, which means the conductivity is approaching infinity. That's why the term usually superconductor, because it superconducts, it conducts with infinite conductivity below Tc. And that was really the very exciting findings by Camerling-Owens. And you can see one critical aspect of this transition is that it is as though the material was following a nice model where you can say that the resistivity of the model is going down as expected with temperature, right? So this part is just maybe you can explain by some root model, but what happens here around this Tc, it's really dramatic, right? It's not like going down slowly or gradually. What happens, as soon as you reach Tc, below Tc, the resistivity all of a sudden, very dramatically or drastically vanishes. And this kind of sudden change in materials property like resistivity, specific heat, whatever you were measuring, this is usually telling you that there is a phase transition, right? What is the phase? Like a liquid is the phase of a matter, solid is the phase of the matter, right? Gas is the phase of the matter. So you can change from gas to liquid, changing the phase of the matter, right? Here, it is as though that when you are above that critical temperature, the material was behaving in such a way that it has certain phase, right? But then this drastic change is telling you that below Tc, the material enters in a new phase of matter. That's why you remember this thing is that the superconductor is a distinct phase of a matter. So when you go below Tc, the material enters in a different phase, which is the superconducting phase, right? And that's a thermodynamic phase of the material. That's the first crucial experimental fact about superconductivity. The next and more fundamental, I have mentioned in the first lecture that although the phenomena like the superconductivity was discovered by measuring this sort of experiment where the resistivity is vanishing, that's why the term superconductivity came, but it's not really the fundamental effect of superconductivity. It turns out that the more fundamental is what is known as the Meissner effect. That's really is only characteristic of a superconducting state. So let me explain what this Meissner effect is. So let's see, we have a piece of sphere, right, a superconducting material, and somehow we managed to cool it down below the superconducting transition temperature. And from this information, you can tell that yes, this piece of superconducting material is now superconducting because the temperature is below the Tc. So let me divide this graph in these two parts, upper and the lower, and then once you cool the sample below Tc, now let's say you apply some external magnetic field, right? So these are the flux line of the magnetic field. What happens, this Meissner effect is telling you is that once the sample is in, right, in this picture, you can remember also T is less than Tc. So this sample is superconducting, and when you are trying to apply some external magnetic field, what will happen is that the magnetic field will not penetrate inside the superconductor. So here what I'm saying is that weak magnetic field do not penetrate the bulk of the superconductor, right? And it is as though the magnetic field is expelled, right? Expelled by the superconducting material. So you can see the magnetic flux are bending and avoiding the superconducting bulk, right? That's one way to understand this Meissner effect. Another way is that, let's say you take the sample, right, and now you are at some temperature which is above Tc. So now your sample is not superconducting. That's why you can see if you apply some magnetic field in the sample, you can see this flux line, they kind of penetrate, right, depending on what type of material you're using, the magnetic field will penetrate, right? So in a normal metal, like the magnetic field, when you apply it, you can see the magnetic field penetrates the bulk of the material. But keep the magnetic field on, and then what you do is that you cool your temperature below Tc. As soon as you go below Tc, what you see is that this magnetic field are expelled from the interior of the superconducting material, right? Now you can see the flux lines are kind of bending away. This is kind of saying the complete expulsion of magnetic field. And this effect where the magnetic field cannot penetrate or expelled by the superconducting material is known as Meissner effect. And this is more fundamental to the superconducting state. We have theories that can explain these things, but right now I am just presenting you with the facts or findings of the experiment. So the Meissner effect is nothing but the magnetic field expulsion of the superconducting material below the transition temperature, right? That's what we know as the Meissner effect. Now, let me introduce the third experimental fact, which is known as the skin effect of the superconducting material. So let me try to explain what's happening here. So let's say we have a piece of superconductor and you're trying to apply, and the sample is in a superconducting state, meaning the temperature is below your Tc. Now if we apply, let's say, some magnetic field in the sample, already the Meissner is saying that it will be expelled. But what really happens is that there is a narrow layer at the boundary of superconductor where the external magnetic field decreases exponentially to zero value in the bulk. So it is as though what's happening is that you are applying some magnetic field. So in this picture you can see the magnetic field is following some exponential fall, right? B0 is the magnitude at the boundary. So in this figure what you can say is that this is your x is equal to 0 point, right? So and then we have some piece of superconductor maybe here along x in this direction. So you're trying to put some magnetic field of strength B0 here. So at the boundary, like there is some small boundary here, then you can see the magnetic field is dying off very quickly. So what happens is that if you go to really in the bulk of the material, you will not see any magnetic field, and that's kind of skin effect, that the magnetic field is really only penetrates in the the slim layer in the at the boundary, right? And that's what explained by this curve where you can have the lambda is critical distance, which is known as the London penetration depth, right? What that means is that at this lambda distance inside the sample, right, when x is equal to your lambda, your height, your magnetic field is already dropped to what? B naught e to the power minus 1. So that's the amount of drop in the magnetic field. And if this penetration depth, the London penetration depth, is named after the scientist London. And it says that the magnetic field, right, only stays in the boundary of the superconducting material, but cannot enter the bulk, right? That's kind of the skin effect. And this London penetration wavelength, the London penetration depth for superconducting material is proportional to this factor, Tc minus T. That's an empirical, experimental based law that the wavelength, the London penetration depth is inversely proportional to the square root of the temperature. And you can see if T is Tc, the lambda is diverging. It means it becomes infinite. So this London penetration depth becomes infinite when the temperature reaches Tc. Try to remember these facts because this will be crucial in the lectures to come. So what is the skin effect? The summary is that if we apply the magnetic field, it will, the first thing is that it will be confined to a very narrow region, and then it will really fall exponentially fast inside the bulk. So if you go in the bulk of your material, you will not find any magnetic field, right? So it's kind of no magnetic field inside the bulk of a superconducting material. That was experimentally kind of found before the BCS theory came, right? So that's kind of the indication that how magnetic field interacts with the superconducting state. And then another experimental observation is that there is an existing critical field, a critical magnetic field. So what I'm trying to say here is that you can destroy the superconductivity using two effects. One is the temperature, right? Because you know, if you go above Tc, if you raise your temperature of your sample, and if it is above Tc, the superconducting state is destroyed because the material becomes normal, right? So that's one way to destroy superconductivity, that you raise your temperature above Tc. Another way is this magnetic field, which is known as critical magnetic field. And this critical magnetic field Hc, which is a function of T, can, if you go beyond this HCT, the superconductivity is destroyed. And that's why there is a critical, this existence critical field. That's why, if you recall, here I told you that a weak magnetic field, because if the strength of the magnetic field is too high, it can be that the strength is higher than this Hc, then the magnetic field can destroy the superconducting state, even if you are below Tc. That's the central point, right? So when your applied magnetic field strength is above HCT, the superconducting state is destroyed. Even you are below Tc, right? So this condition is true even you are below Tc. So there are two ways, right? One is raise your temperature above Tc, that destroys the superconducting state. Another one is that you stay below Tc and then you apply magnetic field, that will, and beyond some critical magnetic field strength, the superconductivity will be destroyed. And this critical magnetic field H is a function of T, is related by the temperature and the Tc by this empirical relation, right? This is an experimentally found fitting relation. And if you plot this curve, this is what you get, right? It's kind of a curve following this equation. And from these two axes, you can see this point where T is equal to Tc, and here where you have Hc at 0, right? So what that means that anything beyond this curve, let's say you are somewhere here, so your temperature is beyond Tc, so you are in the normal state, right? So anything here is normal state. Another thing is that even if you are, let's say, at very low temperature, So you are in the superconducting state, but now you are increasing your field strength, right? So that's your magnetic axis. So you are increasing, and if you go anything beyond this HC0 at t is equal to 0, the material becomes normal again, right? But if you stay in this part of the curve, right, you will be in the superconducting state. But anything beyond this, any point beyond this, right, beyond this curve is a normal state. So that's the existence of critical magnetic field, and this is an experimental fact that was discovered way before the original BCS theory came in 1957. So these were really some clues that how we can kind of understand about your sample, what's happening inside. And then let me introduce with you with the fifth experimental fact, which is this persistent current and flux quantization. So to explain this thing, let's consider we have a ring of some superconducting material, but right now T is above Tc. So although the material is in normal state and you are putting some magnetic field, and these are the flux lines of the magnetic field, right, in this direction. Now with the magnetic field on, what you do, you just go below Tc. That's what happened. Let me explain you what's really mean by this picture. So if you recall in the Ampere's law, it says that when you have a magnetic field in this direction, right, current must be circulating in this loop. So that's a normal metal, let's say maybe an aluminum or something. So there should be a current in the loop, right, because the magnetic field is in this direction. So this will generate a current that's kind of circulating in this loop, right? Now this loop is in normal state. So you're applying some magnetic field, you have some current. So as soon as you go below the Tc, the question is what will happen for this current, right? Do you understand that? So once the material becomes superconductivity, now when the ring is superconductor, what is the resistivity? Resistivity is 0, right? It means you don't have any resistance in your wire. If you don't have any resistance in your wire, what is the loss, which is I square R? That's also 0. So you made some current by applying some magnetic field, and then you bring the sample below Tc. Now you can see even this current cannot stop, right, because we don't have any loss. So if the ring is lossless, the current will still be flowing, right, because it's a superconductor. And that's really an important understanding. That's why it's known as the persistent current, because it persists even when you shouldn't have any current here, because we just bring the sample below Tc. Now as the current is flowing in this direction, you can understand there should be some flux, right, because that's the Ampere law, that the current produce magnetic field and magnetic field produce current, right? So when you are below Tc, the current will keep flowing, and what happens is that you will have some flux, right? That's the effect of persistent current. And more interestingly, there is also this phenomena which is known as flux quantization. It means that inside this ring, right, the magnetic fields are kind of trapped. Why is trapped? Because the current is flowing here, and why it cannot reach and then cross the superconductor? Because you know magnetic field cannot penetrate inside superconductor, right? So that's the way, that's why these fields are kind of trapped inside the ring, because they cannot come out like crossing the superconductor. That's not allowed, right? And on top of that, the amount of flux that this ring can hold is not any number, rather a multiple of this quanta. This is known as the flux quanta. H is nothing but the famous Planck constant, 2 is just a number, E is the charge of electron. So the important point here is that in a superconducting ring below Tc, the amount of flux is quantized. take it as experimental fact, and we will explain these things later with using some model like the Landau-Ginzburg model or the BCS theory. But here, take them as a fact that inside a superconducting ring below T is less than Tc, the amount of flux is quantized, and the quanta is h by 2e, right? The smallest amount is h by 2e, then it should be h by e, right? It's always some factor of this, then times 3. So it's always a factor of h by 2e. That's known as flux quantization. So this is another experimental fact about this superconductivity. On top of that, there is another experimental fact, let me introduce here, which is the specific heat phenomena. And what is specific heat? You remember, right? You want to raise the temperature of your sample, and you are putting some energy in the sample. You ask that, what is the amount of energy, let's say Q divided by del T, right? So what is the amount of energy we need to increase the temperature by some 1 Kelvin is your specific heat, right? From your first year physics courses. And this specific heat is always a measurement probe for any experimental condensed matter physics experiment. If you see some new phenomena is occurring, this is one of the very common experiment that people perform to understand what's happening inside the sample. So for a superconducting material, right, you measure the specific heat as a function of temperature, and you see what's really happening here is that this part of the curve is linear, right? So when you are above Tc, it seems that your specific heat is linear in T. But as soon as you go below Tc, there is a sudden jump or a discontinuity, right? So we have a peak here, a sudden jump, and then the specific heat does not follow this straight line anymore. So below Tc, the specific heat of the superconducting state, the subscript S for superconductor, so the specific heat in the superconducting state below Tc follows this exponential fall. So which one is falling faster? Definitely this exponential curve. And if the material were normal, we expect the specific heat to go linearly all the way up to T is equal to 0. But for superconductor, that's exponential. So this is another signature of superconducting material, is that exponentially suppressed specific heat. At low temperature below Tc, the specific heat is not linear, it's falling exponentially fast, right? So just let me make one comment, although this is not the proper place to explain this thing, but just take it as information, is that what do you really mean when you say that the specific heat is exponentially falling? It means it is really difficult to give energy to the system, right? When small specific heat means you are really struggling to raise the temperature of your system by inputting some energy, right? Why the specific heat is low is because you are really struggling to put energy inside the system. That's another kind of physical understanding why exponentially suppressed or exponentially small specific heat physically means. It means that it's difficult to input energy into a system, and that kind of indication about something really very special of the superconducting state, that maybe in the superconducting state something is happening that kind of makes the energy input of the system difficult, right? And we will see in some lectures to come is that it kind of technically it means that there is a gap in the excitation of the superconducting state. This statement I don't expect you to understand at this moment, but remember that I have mentioned that this exponentially suppressed superconducting specific heat is a kind of indicative that there is something very special about the energy spectrum of the superconducting material. Okay, and I think the isotope effect is the last experimental fact that I want to mention before I finish this lecture. So we have in total 7 different types of experimental findings about the superconducting material, right? And this isotope effect, let me just explain what I have written here, is that the critical temperature Tc is proportional to the square root of the m, right? And what is m? That's really, it's the ionic mass of the system. So these experiments came a bit later because you need a really precision measurements to find this effect, because the Camerlingon himself measured this experiment, performed this experiment around 19, if I'm not wrong, 22, but he really didn't see this effect because his resolution, his experimental setup doesn't have the energy resolution to measure this. But later, some other people really showed that the transition temperature of a superconducting material depends on its ionic mass. And what I mean by that is that, let's say, let me explain this ionic mass here. So let's say we have our mercury here, right? And then let me draw a table where I will denote the number of electrons and the number of neutrons in the system, right? So mercury, the basic element, has 80 protons or 80 electrons, and then we have 121 neutrons, right? And the mercury has different isotopes. So this is like our 200, but mercury have different isotopes, right? So let's say we have 198, we have 199, we have 200, and I'm just giving you some examples, 202, we have mercury 204, right? So mercury has different isotopes, and we know every one of them will have same number of protons and electrons. That's not a problem, always 80. But what differs is the neutron number, right? So, and they have different, let's say here we have 118, here you have 119, here you have 122, here you have, for 204 you have 124, right? So the fact is that if you take different isotopes of the mercury, right, and measure the transition temperature, this m is the mass of these isotopes. That's the finding. And why I'm calling this ionic mass, you will understand, because let's say we take a sample of mercury where this one has helium 200 and this one has helium, let's say, 198. So inside the sample we will have the helium ion and some electrons, right? We will have some helium ion and some electrons, and the electrons. So that's the, let's say, the nucleus, and around the nucleus we have this number 80 electrons. So this is our helium, sorry, the mercury 200, and maybe this is the mercury 100 and let's say 98. So in these two samples, what is the difference? We have 80 electrons, we have 80 electrons, we have 80 protons here, 80 protons. The difference is the number of neutrons. So you can see the nucleus is different, right? And in every material, if you take 1 or 2 electrons which are kind of wandering around, what left is the ion with some electrons and the nucleus. So here you can see, as their nucleus are different in these two samples, what really different from between these two is the ions, right? So that's why the isotope mass is the ionic mass difference. So that's why usually we call this ionic mass, because the ions are different, because the nucleus is different. And why nucleus is different? Because they have different number of neutrons. And the experiment suggests that Tc is the square root of this ionic mass. And let me tell you, this experiment really helped to understand the superconducting state in a microscopic using a microscope theory, because so if you remember, if the transition temperature is varying with the ionic mass, and you remember that, right? How do you model ions in the solid, right? If somebody asks you that, how do you model ions, because they vibrate, right, when the temperature is there. So the ionic vibration is nothing but phonons, right? And these experimental results kind of indicated that there has to, because the Tc is varying over the ionic mass, there somehow the phonon is involved in superconductivity. And that was really a crucial input to the experimental like the experiments on the superconductivity, is that how the superconducting transition occur. Phonon is one of the crucial factor to understand this completely new phase of the matter. So I think in this lecture what I tried to give you 7 different experimental findings about superconducting materials to understand why this phenomenon really occurred. That's like a way different story, because you need a model, right? And if you look at the history, people really tried hard, like London brothers, right? They came with their phenomenological theories to explain all of these effects. And then you will see that Landau and Ginsburg proposed their model, and then BCS came and they kind of tried to explain everything with a macroscopic view. So understanding superconductivity can be exceedingly difficult, because you really need very advanced formalism in condensed matter physics to understand everything. Why, if you ask the question, why these experimental facts are there? But for us, the important thing is to remember that if you have a superconducting material, these 7 experimental facts will be valid for that kind of superconductor. And that's these effects are really important to remember to study superconductor, right? Because although we will not be capable of, right, explaining everything with the proper theory in this course, but the crucial understanding and the crucial experimental facts about these superconductor materials can be kind of these 7 experimental facts. So remember them, and as we go along in the future, we will try to understand some of these experimental facts, why these effects occurred in the material, right? And I think for this lecture, that's about it, and thanks for listening.